Okay, let's look at 13.3, equations of motion for a system of particles, system being the key word here. I'm going to read some excerpts from the chapter. It's actually a pretty short chapter. Okay, so the equation of motion will now be extended to include a system of particles, and these particles are isolated within an enclosed region of space. So I'm going to draw this system of particles as a blob, and this could represent a liquid or any fluid, or a gas, not any, but we could use them to analyze these systems. Draw a couple more particles. Alright, I can draw a position vector out to what we'll call G. That's our center of gravity, we'll call it. And we'll call this R of G. Okay, now what we have to imagine is what happens to the ith particle. Alright, so at the instant considered, this arbitrary ith particle having a mass m is subject to a system of internal forces and a resultant external force. The internal force, represented symbolically as Fi, is the resultant of all of the forces of the other particles exerting on the ith particle. The resultant external force, big F, represents the effect of these other forces between the ith particle and the adjacent bodies, which are not included in the system. I know that may sound a little hard to digest, but let's just take a look. If we have external forces, I talked about the Fi lowercase first. This is maybe all the forces acting inside. This is the internal resultant force, and we could have some external force also, the capital. Alright, now what this says is that when we sum up the forces, and that's equal to mass times acceleration, that we also need to include the summation of our internal plus the summation of our external. And that's going to give us the summation of our particle I and the acceleration of particle I. So if I take this diagram right here, I have some particle. We had a force coming in and some internal force. Alright, if we turn this free body diagram into a kinetic diagram, that would be multiplying by mass and adding those vectorially. We get something like this. Point it down a little bit more, probably something like that. Okay, now, are we going to use that much in this class? Not as much as you would in something like fluids. What we're going to be looking at more is the center of gravity, and I'll get to that in just a moment. But what's important is if we look at all these internal forces and we sum them all up, the summation of the internal forces is equal to 0. And I had a problem given to me on my physics qualifier, and it was a pulley mounted to the ceiling, and a guy or gal was pulling up on the string, and they wanted to know what was the force equal to required to pull it up. Well, we wrapped our heads around this forever, because like if you imagine pulling up, that's going to push your body back down into the floor more. How do you account for that? Well, those end up all being internal forces, and we can just draw a box around this thing and call it a system. And since the tension is uniform anywhere, he is pulling up the same amount as his tension to keep him from moving. So we can ignore these internal forces and only the sum of the external forces will be considered. Therefore, we will write the summation of the forces internal is equal to the summation of the mass internal, acceleration internal. Now, I already located this position vector. I should have located the ith particle too, or I. That center of gravity is now what we're going to look at. All forces need to go through the center of gravity for the time being. This will cause it to accelerate. If we had an unbalanced force acting some distance away, this would cause some sort of rotation, and we're not ready to deal with that yet. Okay, so if RG is then a position vector which locates the center of mass of the particles, then by definition we can say the center of mass is equal to the summation of all those other particles put together, where m is equal to the summation of all of those particles. Okay, differentiating this equation with respect to time, assuming that no mass is entering or leaving, gives us mass times the acceleration of gravity is equal to the summation of all those internal masses and their internal accelerations. And we can substitute this back up into here and get the summation of the forces is equal to, that's a vector, is equal to mass times this acceleration of the center of gravity for that object. So, until we get to chapter 16 and 17 and further, we are going to be looking at forces that have to be concurrent through or pass through the mass center. Otherwise, a rotation will occur, and we don't know how to deal with that just yet.